So today we're going to talk about the different ways we can algebraically manipulate Taylor series. So basically just applying different arithmetic rules to help us figure out different things. Yeah, very specific right there. So one of the first things that Tom mentioned was how you can add and multiply, use addition and multiplication to figure out the Taylor series for functions that have something that looks similar but are like there's like a little complexity to it. So for example, if we know what the Taylor series of sine x is, which is in here, and the function itself multiplies sine x by x squared, we can just use basic algebra where we can, since sine x is being multiplied by x squared, every term in the Taylor series of sine x can also be multiplied by x squared. And when you do that, you effectively find the Taylor series of sine x times x squared. And with that, if you want to, you can also write out the summation, write it in summation notation, which is basically like this. X squared is being multiplied by the original summation notation of sine x, and you would end up with something like this. So, in other words, with two functions, when your function consists of two separate functions, you can just use basic arithmetic rules to modify the series. And then the next concept we talked about was substitution. So if we have, in the example like e to the negative x squared, we know what e to the x is. We know the Taylor series of that, but we don't know exactly what the Taylor series of e to the negative x squared is. So we can kind of go back to when we used to the concept of substitution and when we're integrating or like just substitution in general. So we can say that negative x squared is equal to some variable, and that can be any variable you choose, and then you write out the series as if z were actually part of the equation. So you just write out the series like this, and then eventually everywhere you have that variable that you chose to use as a substitute, so in this case would be z, you just rewrite the original thing itself. This way you actually also you get this modified Taylor series, but it's like actually correct. And then finally we have we can use differentiation and integration. So if we have two functions and we know that the relationship between these is that one is either the derivative or the integral of the other, or the antiderivative of the other, then we can use that relationship to figure out the derivative or the integral of the Taylor series of that derivative or integral. So in this situation, 1 over 1 minus x squared is the derivative of 1 divided by 1 minus x. So if we know what the Taylor series of 1 over 1 minus x is, to find the Taylor series of 1 over 1 minus x squared, we can differentiate both sides. So this is the derivative of that, and then you can derive every term in this Taylor series to find the Taylor series of 1 over 1 minus x squared. So for today's video, we want to talk about this one problem here and try to figure out as a group. So we have to find the 7th degree Taylor polynomial for the integral of sine x over x. Yeah, let's begin. Could you pull up your whiteboard?
Quick question.
Wait,
I thought we were finding just like the Taylor series
the
expansion.
Taylor expansion. Does it say the 7th degree term? Because in the
I don't think so.
is that on his slide or because on the Moodle page it just says Taylor series expansion for the function. Or the
I guess not specifically, so we don't have to do 7th degree, but I don't think it's that much more work. So you just plug
right.
in.
Okay.
Because yeah, but
I think the 7th degree
let's just try to do this first.
Yeah. Sure. So we write out the function.
All right, so do you remember the exact?
Yeah, integral of If you just write out the integral first.
Oh,
I can tell you what the power series is, so you can write out the terms easier if you want.
it's this, right?
Okay, cool.
Yeah.
Yes.
So the Taylor series for sine of x written in summation notation would be n equals 0 to infinity, and then I'll tell you what the other part is. Yeah. And then it's -1 to the n divided by 2n plus 1 factorial multiplied by x to the 2n plus 1.
Okay.
So yeah, we can use what we know about that. Since we can basically algebraically manipulate this. If this is sine of x, then we can just divide every term in here by an x, which will get us the same thing, but instead of 2n plus 1, it's just 2n. It's x to the 2n plus 1, but just 2n. But I also feel like, can we also just, if we try to integrate this, is that going to be hard?
Well, we can integrate. We can do it term by term.
Yeah, we can just find that. Yeah,
But-
I like that idea better.
But if we
Yeah, I feel
integrate it,
integrating
if
there.
we integrate this itself, we can find what we can find what any term is.
Yeah, any term is, yeah. That's true.
But I'm just wondering if,
I mean,
if
half-
it's gonna be if it's gonna be significantly harder.
I think it will be. It looks like it will be. 'Cause what are we
I mean,
gonna?
have fun
we have two
integrating.
variables here.
Yeah,
Are we
Yeah.
gonna integrate it with respect to x or to n?
that's a good question too. Yeah, I feel like if we just do
I
it
think
term
we
by term,
integrate
because
with respect to n.
I think it'll be easier if we just do like 4 terms.
Yeah,
We can integrate them into.
we can do that.
So we can do like x equals 1. So that's gonna be.
Well, we would start with x. Yeah.
Oh, x or n equals 0. You're right.
Yeah,
Well, technically, what am I trying to say here? So we could do n equals 0, but this is an odd function, so it's just going to equal 0.
Is it still gonna equal 0 now that the exponent's changed?
Oh, good point. Yeah, maybe. Yeah, sorry, 0 because it's different now.
Let me see, because this is gonna be 1 over 1 times.
wait,
x
just
squared.
write it out. Just
Oh,
write it
it's
out.
gonna be. I think this is gonna be x squared.
Sorry, what was the question?
So are you guys working on integrating the Taylor series approximation for sine of x over x?
yes.
Yeah.
So I think what I would do is, instead of leaving it in summation notation, which is going to be a little hard to integrate, I would write out a few terms of what,
Yeah.
like write out the first few terms.
Yep. So
So
let's see. If it were 0, -1 to the 0 is 1.
yeah, 2 0 plus 1 factorial times x to the 0.
Which is 1.
So it's just 1.
So -1 over negative 1, right?
No, -1 to the 0th power is 1.
Oh, this is
Yes.
1. You're right.
So
Right. So
the
just
first
1
1.
over
Okay.
1 times
1
1.
over 1.
Maybe 1 plus
1 over 1 times 1.
and I guess
Cool.
when
The
it's
Brains.
1 can be
squared. So it's gonna be 4 plus 1.
Wait.
wait,
Um,
squared. Wouldn't
Yeah.
it be just
To
to
the
the 1?
first
Oh wait,
power.
oh, it's the 1. We started with 0.
Yeah.
Whoops.
I thought that, wait a minute.
Whoops. 1.
And then the 4. I mean, 4 would be a 2.
2.
Yep. 2 plus 1.
And then x
Factorial.
squared.
X squared.
Mhm.
Which
Yeah.
is gonna be
Negative
Negative
x squared
1 over 6.
over-
Is it 6?
Yeah.
3
Three
factorial. Yeah, okay. So negative x
So,
squared over
x
6.
squared over 6.
Negative x squared
Yeah,
over 6.
cool.
So now we can do 2. So negative 1 squared over 4. Now it's over 4 plus 1 factorial
Mm-hmm.
times
5
x
times
to the
5
4.
times 3 is
There'd be x to the 4th over 60?
60. Yeah.
Is this still
Yeah,
is
yeah.
Oh yeah. Okay. X to the 4th over 60.
60? Wait.
So
Oh,
yeah,
Yeah,
it would be 5
5.
yeah,
factorial.
yeah.
Yeah.
I know. I was just like, wait. Yeah, 60.
I guess we can do one more.
Mm-hmm.
Yeah, sure.
Because this is gonna start getting ridiculous after a while.
Mm-hmm.
So it's gonna be negative 1 cubed over 6 plus 1 factorial times x to the 6.
Let me get my calculator real
7
quick.
factorial.
Right, I said,
I think.
what's it? 7 times 6 times 5?
Yeah, it's
We know it's gonna be
50,
negative.
40.
At least.
It's totally fine just to leave it in factorial notation, by the way. You
Oh,
don't have to
oh,
evaluate
okay.
it.
Oh,
It's a constant.
Leave that one. Leave that one in
You can just
factorial.
write yeah,
Oh no, it's
oh wait,
Yeah.
7 factorial.
or just 7.
Yeah.
Yeah.
yeah, that's completely fine.
Cool. Oh wait,
like-
because I forgot when you integrate it, you take it out of the integral anyway, right?
Yeah.
Coefficient. Okay.
So you can only like factor out a constant from the integral if, every term in the integral is multiplied by that constant. But you can think of integrating each term separately.
Right. Yeah.
Okay, so
and then
this
okay,
is
yeah,
gonna
yeah.
be. Oh wait, and then
X to the. Oh wait, yeah, that's right.
so integrating this, it's gonna be x plus.
You skip.
Yeah.
So,
I mean,
so
we're
if
just-
you take out integral-
1 6.
Yeah, it's gonna be
Yeah.
negative 6 times
um,
x cubed over 3
Mm-hmm.
yes.
plus 1 over 60 times.
X to the 5th over 5.
Yep.
Mhm.
Minus 1 7 factorial. Looks like a 7. Times x to the 7 over 7.
Cool. I'm gonna stop recording.